Now let's see how to debug this device. First, turn on the sensor. For the already connected sensor, we can simulate a damage signal of a steel wire rope. We can prepare a few common tools. One is the paper clip, which is commonly used in the office. We can pull out a piece of wire, just one end of it. We can also find a hardware store and buy a slightly thicker iron wire. The third item is a screwdriver, which we commonly use in daily life. For these three items, we will mainly focus on how the instrument reflects the damage to the steel wire rope. Now let's open the software. Double-click the software on the desktop. We already have port 3, so we won't make any selection. Now we choose a parameter 13. We will sample again when sampling starts.
选择一个参数13，好，我们再采样。
We do the same thing. We roll the wheel. First, to see if there is a good signal. Yes, there is. We exit. We are now officially starting to simulate a sampling process. Let's first look at the effect of a paper clip. Now, let's take a paper clip and draw it synchronously. This is the lower half of the brain cover. In the upper half, let's take a look at the manifestation of a damage signal. When there is no damage, it is a straight line graph like this. We can use another tool, a slightly thicker wire. And let's take a look again. The above is a comprehensive test that can be done. Obviously, the damage signal is larger than the one from the paper clip just now. Let's try another batch. We see the third screwdriver, which has a larger damage signal. Let's take a look. When there is no damage signal, everything is normal. And then we save the data. The fourth step involves saving the data. We can save the data by date or by name. It doesn't matter actually. We are just doing sampling and data analysis on site. The analysis is all done back here. We can conduct a simple analysis. We can see that at the beginning, the damage signal is relatively small. Then in the middle section, the damage signal is slightly larger. This is a wire. And the front part is a paper clip. This is the signal of a wire. The blue part represents when there is no damage signal, and the straight line segment is relatively intact. When we see a larger damage signal, it looks like this. Let's analyze it. Automatically, we'll just analyze it. When it automatically analyzes, it thinks all the damage signals above are leg. Let's look at the report. It can produce a single report. This is the last step to give us a result. That is, we can do it based on the number of wires, or based on the percentage the number of wires is. For us to know the damage situation, then the percentage of the cross section is a standard in our industry, which can be used as a reference to define whether it's scrap or not. For example, in coal mines, 5% means no personnel can be lifted, and 10% means no materials can be lifted. Different industries have different standards. This is the date when we conducted the inspection. Then the number of meters inspected, and the diameter of the steel wire rope inspected. Here is the serial number and the position of the steel wire. We mainly look at the cumulative number of wires. Within the lay length, we can look at the part with less damage earlier, which it thinks is 1 or 2 wires. Then we can see that by the end, we recorded that at the end, which is our screwdriver part, it can be considered more than 10 broken wires. This is related to the parameters we set, which can be adjusted. We can simply take a look. Okay, that's it. Now let's take a look on our experimental platform. We have a fixed steel wire rope. We can simulate the damage signal on the experimental platform. Let's first take a photo of a simulated broken wire in the steel wire rope. The rest of us are in good condition. There is a broken wire here. We can check if there is an alarm when the sensor passes by. Let's open the software instrument first. The instrument is already connected, and the device is also connected. Okay, let's open the software. The port is set to the default 3, so we don't need to select it again. First, let's choose that my steel wire rope is 13. On the standard platform, one thin rope is 13 and one thick rope is 28. Let's simulate it first. Select a parameter of 13, and then start sampling. I'll demonstrate the damage detection feature on a device that identifies on hand. Let's first take a look at what it looks like. Let's look at the computer. When there is no damage, it only shows a blue curve without any peak appearing. Now let's see what happens when there is damage. The repeatability is very good. Let's take a look. Once you pass this point, an alarm will sound. I'll pull it back and forth here for demonstration. Then we just need to save the data. After saving and analyzing the data, we can see that when there is no damage, it is a blue straight line. When there is damage, it is a small peak. It has very good repeatability. You can check the position. That's all for our demonstration on the experimental platform. Next, let's take a look at amateur test bench. We will simulate a situation where the motor is driving while the sensor remains stationary. Let's focus on that small motor test bench. Our motor test bench uses seamless steel wire ropes. Let's take a look. There is no damage on it. It is manually made with a boundary. Let's first see if it can be detected by the naked eye at that time. We will then see if this instrument can detect it. Let's connect this device first. Now we open the software and select a parameter. Current line. It says 13th rope. We select a parameter and confirm it before taking a sample. I'll start here, and then check the test bench over there. I'll turn on the motor. Let's take a look at the movement process of this steel wire rope. I'll turn on the motor. The repeatability is very good. The boundary part, where the steel wire ropes are intertwined, has internal damage, which can be detected. This is where our detection system can see what the human eye cannot. That's all for the demonstration.